So I want to go to page 5, part D. And I think part D is good in the sense that it's allows us to kind of explore these important concepts, or at least see relationships between these important concepts. So before we do part D, let me just give you a just some background information here. Now, let's say I had a graph that is concave up. Okay, so let's say I had a graph that's concave up. And so I know the graph looks like this. And let's say there is a point on the graph that I'm provided where with the function, I can find the derivative. From the derivative, I can find the slope. And then with the order pair and slope, I can create my tangent line equation. So let's say I have a tangent line equation. Right. Now, let's say I have information about 2 points on the graph where I can create a secant line equation. So secant line equation, it just means a linear equation that happens to go through 2 points on the graph. Okay. So they don't have to be parallel or anything. I just want to kind of show that some relationships here. Now, to get to the tangent line equation, all I need is order pair and slope. To get to the secant line equation, same thing. I just need any order pair, and then, but I don't need any calculus because I can just pick off any 2 points here, find the slope, and then do point slope form. Okay. Now, let's say I wanted to figure out using the tangent line and secant line. Let me identify them here. This is my tangent line. This is my secant line. Secant line just means a line that goes through 2 points on the graph, or more than 1 point on the graph. Okay, let's say I wanted to know what this value was on the graph. Okay, obviously I can just put that value into the curve and find that x value, find that y value. But let's say we want to use the tangent line and secant line to approximate that value on the graph. So if I want to do the if I want to use the tangent line to approximate it, it'll give me this value. And obviously this value is not going to be the same as the exact value. But what type of approximation will this be? Will this under or over approximate? Under approximates. Okay. What about if I were to use the secant line to approximate this point at this x value? It will what? Over approximate. Okay. And this is going to be always the case if the graph is concave up. Okay. Your secant line will always over approximate the actual value, and your tangent line will always under approximate the actual value. There's no need to memorize this. If you just sketch this graph out, you can visually see it. What if the graph was concave down? Opposite, yeah, opposite. So if I have a curve that's concave down, any tangent line is going to skim above the graph, right? It doesn't matter where that tangent line is. It's always going to over approximate any point on that curve. And then any secant line is going to under approximate, right? Does that make sense? So if I want to compare these 3 points here on the graph, this is the exact value, over approximation, under approximation. Right. So we're going to take that knowledge, and I think that will make part D make a little bit more sense in terms of how we're going to approach it. So part D says, suppose that f prime of 5 is equal to 3. So we know that at 5, there's a slope of 3 on the curve. Okay. And f double prime of x is less than 0. What does that tell us? The graph is concave down. Okay, concave down on the closed interval from 5 to 8. Okay. So with this tangent information, we can take this and the order pair and create a tangent line equation out of it, right? Because let's say this is the curve here. The curve is concave down. Since graph is concave down, a tangent line we know is going to sit above the graph. So we can gather information to get our tangent line. So our order pair for the table is 5, -2. We know the slope at 5 is 3. So you take your order pair and your slope, you build your tangent line equation. y equals 3 times, y minus 2 equals 3 times x minus 5. So let me read the rest of the problem here. Using the line tangent to the graph at x equals 5, show that the actual value on the graph is less than or equal to 4. Okay, we don't know exactly what the exact value is. All we know is that the graph is concave down. But we know that our tangent line is going to over approximate. So if I plug 7 into the tangent line equation, I'm going to get 4. So if my y value is already sitting at 4 for my tangent line, I know that my actual value is going to be where? Below it, right? So that's what we're able to show. Since the tangent line, which is over approximating the actual value, is already at 4, we know f of 7, the curve at that point, or the point on that curve, is going to be lower than or equal to 4. Okay. Moving on here, it says use the secant line to show that f of 7 is greater than or equal to 4/3. Well, if I can show that the secant line is actually at 4/3, as a y value of 4/3, then I can guarantee, even though I don't know what the rest of the graph looks like, I know that my secant line is always going to sit below the actual point on the curve. So how do I get my secant line equation? I can use the order pair that's provided me. They tell us between 5 and 8. So those are my x values that I can use to help me find my slope. So there's my order pair, 5, -2, and 8, 3. Find the slope between those 2 points. And that's going to give me 5/3. Does it matter which order pair I choose for my point? I can choose 5, -2, or I can choose 8, 3, right? Same thing. Your equation will look a little different, but it's going to be the same equation ultimately. Okay. And then I get my secant line equation. I plug 7 in, and then I get 4/3. Well, if my secant line is giving me a y value of 4/3, then I know for sure that my actual value must be above 4/3. Okay. So I think this problem kind of is a way for us to understand that relationship between secant line, graph on the curve, and tangent line, and that if the graph is either concave down or concave up, the relationships are going to flip-flop in terms of which one is overestimating, which one is underestimating. I think some students have questions about part D for number 6. So page 6, it says a light is directly above the western end of the track. Then brides so that at time t, distance L of t is given by L of t squared. At what rate is the distance between Ben and the light changing? So ultimately, we're looking for L prime, right? L prime is going to be the rate. Well, all this equation, so basically we're trying to find L prime of 40. Now, this is stuck inside the bracket, so to find the derivative, we got to go through chain rule. So bracket square becomes 2 bracket times inside function derivative, so L of t becomes L prime. 12 squared goes to 0, and then b of t squared becomes 2 b of t times b prime. Okay. L of 40 you can gather by plugging 40 into the L of t equation. L prime of 40 is what we're looking for, so we'll leave that blank. B of 40, we can pull that from our table. And then b prime of 40, we can also pull that from the top. Yeah, so b prime is basically b of t. So over here, L of 40, I just plugged 40 into L of t. So I do have to step away and kind of gather that information. But once I have L of 40 being 15, then I just plug everything into my equation, right? And I think we've had practice with this type of chain rule and function notation with the previous FRQ, right? You understood how within chain rule for something function notation, the best we can do is just call a derivative L prime or B prime or of that function values or that function notation's derivative. Okay, so then once we have everything identify for everything except for L prime of 40, we can just isolate L prime of 40, divide both sides by 30, and then we get 1.5 meters per second. Okay, I like to spend today in class. Tomorrow I'm going to be checking pages 7 through 10. But I feel like 7 and 8, I think you guys will be able to handle because you've seen Barkov motion and Riemann sums, both Barkov motion. Just keep in mind that this is question 4, so this is meant to be done without a calculator. Okay. Same thing here, page 8 this is number 6. Anything that's 3 through 6 is non-calculator, which means that you got to do all this by hand. So if I want to find the acceleration, I have to find v prime. I got to work this out by hand. I got to do chain rule. If I want to find the position, I have to take the antiderivative, and I got to go through U substitution as well. So we got to show the work if something is non-calculator. Okay, so what I want to do is I want to go back to some of these antiderivative word problems. So let's do page 9 and 10. We'll do those together in class. Okay, notice this is question number 2. So this is calculator active. A water tank in Newton holds 1,200 gallons of water at time t equals 0. During this time interval from 0 to 18 hours, the water is pumped into the tank at a rate of W of t. So this is gallons per hour. So there's water in the tank, water is coming in, and then also water is leaving at a different rate. R of t equals 275 sine squared t over 3 gallons per hour. Part A says, is the amount of water in the tank increasing at time t equals 15? Well, we want something in terms of a rate. Well, we already have something in terms of a rate, so we just leave it in this form. So all you do is plug 15 into WT and RT and see which one is higher, right? If WT is higher, then what's happening to the water level? Right? If the rate at which water is coming in is higher than the rate at which water is leaving, what's going to happen with the water level?
It would increase.
It's increased, right? But if RT is greater than WT, then the water level is going to do what? Decrease. Okay. So basically, all you need to do is just to do WT minus RT, right? And just see which one wins out. Okay. If I get a positive value out of this, I know I'm going to be that the water level is going to be increasing inside the tank. But if R of 15 has a higher value, then we're going to get a negative out of this, and a negative would indicate that water level is decreasing. So we can enter this into the calculator. Now, the notation here, this is shorthand form. We cannot enter shorthand form into the calculator. So how am I able to represent this square inside a calculator? I got to put it outside a set of parentheses, right? So, I see some students, struggling on the test. They're like, where's the notation for me to put that square between the sign and my variable? There is none. Okay, so you're going to have to just know that that square is a shorthand form. It really means the expression is being squared. So in your calculator, practice entering that in. I have y1 holding W of t, and then I have y2 holding R of t. And again, you're always using variable x in your calculator. So once I have y1 and y2 holding W of t and R of t, then if I do alpha trace y1, I can just plug 15 in that way, and that the calculator is going to know, okay, you want 15 in for all the variable within the expression, minus my R of 15, alpha trace y2. Okay. We get a negative number out of it, so that indicates to us that water level is what? Yeah, going down. Yeah. I said not increasing, but I could have just said decreasing. But it's the reason why was because it says is the amount of the tank increasing. You either say it's not increasing, or you can say it's decreasing because that value is negative. That rate is negative. Part B, to the nearest whole number, how many gallons of water are in the tank at time t equals 18? So if I want to figure out how much water is in the tank, we use the formula that we've seen before, right? Any amount, any final amount I'm looking for, there's going to be three things I got to consider. How much is in the tank initially, how much has been added, and how much has been removed, right? Combine those values, I'm able to figure out how much is left inside the tank. So I want to create a formula first before I find the exact moment in time that they're asking for. So I'm going to say a of 0 is my initial amount, integral from 0 to t. I want to give that flexibility with my upper bound for future purposes. And I say w of x because I just want to use a different variable so that after the antiderivative, that t can plug in for the x. So I don't want my upper bound and my integrand to share the same variable. So I have to call it w of x. Okay, minus the integral from 0 to t of r of x dx. Okay, so now that we have our formula sets, we can now adapt the formula for this particular problem. So I want to find a of what? Yep, a of 0, but ultimately I want to find a of 18, right? So replace every t with 18, and the rest can just go in the calculator, right? So we know that there's 1,200 gallons of water in the tank, plus the integral from 0 to 18 of w of x. This is going to accumulate my rate. My w of x is gallons per minute or gallons per hour. My dx is also out is in terms of an hour. So I know that if I multiply a rate with the time, that's just going to give me a unit of gallons. So that's going to give me how many gallons has been added to the tank. This will give me how many gallons of water has been removed. I combine those values together, and I have 1310 gallons remaining in the tank. Okay, part C, at what time between 0 and 18 is the amount of water in the tank at an absolute minimum? So what is that hint for us to use? Absolute minimum. EBT, right? Extreme value theorem. Anytime we're trying to find the furthest right, the furthest left, any extreme values, max or min, that's an indication that we want to apply EBT. So EBT means we got to test endpoints and we got to test what? Critical points. And how do we find critical points? Set what equal to 0? Derivative, right? So I have a of t, right? This is my function. So it's nice to build this function because we know we can use it and we can also adapt it to find the derivative. So let's build the derivative here. A prime of t equals, this goes to what? It's the derivative of a of 0. What's the derivative of my initial amount? To 0, that's a constant, so that makes 0. What's the derivative of this integral from 0 to t of w of x dx?
W of x.
Okay, yeah, almost w of t, yeah. So basically, we know this wipes out, the upper bound gets inserted into the variable. So w of t minus r of t. Okay, so that's my derivative equation. And that is going to be how I'm going to find my critical points. I'm going to set a prime of t equal to 0. So these are messy functions, right? We don't want to be working this out and working this algebraically. We just want to make the calculus do it for us. So if I understand that whatever makes w of t minus r of t equal to 0, That's going to be where my critical point is. And if I know my critical point, then I want to test my critical point against with the other candidates. Okay. So what I want to do is I want to graph that W of t minus R of t. Well, the nice thing is I already have my R of t and W of t in my equation, in my calculator. So I can just create a new curve and call it W of, sorry, it's hard to see, W of t minus R of t. So under Y3, I just called it Y1 minus Y2. And notice that I went and I unhighlighted Y1 and Y1 and Y2 because I don't want to see all these graphs showing up. I just want to see Y1 minus Y2, and I just want to know where am I going to see the x-intercepts, right? I want to see it hitting 0 and crossing over 0. Now, I wouldn't do zoom 6 with this. If you do zoom 6, it's going to be, I can show you. All right, it just, there's too much going on. And we're zoomed in too far. If you see a vertical line, that means you're zoomed in too far. So we can go to the window. We can adjust our X-min, X-max. Now we look at our information here. Our t values between what? 0 and 18. So that means we only need to see our x value from 0 to 18. I just want to say 20, so I can just see around my corner here. I don't want it right up against mine, but it's up to you. Now, Y-min, Y-max, if you look at your coefficients of your problem are in the hundreds. So that's going to really push the graph up. So you should kind of play with different numbers here. Just try to match numbers that are in that range. So I would say negative 200, 200. I mean, you can choose negative 100 to 100. It's really doesn't matter as long as you can see the graph comfortably, and you know how to play with your window. So you're only playing with those 4 numbers: X-min, X-max, Y-min, Y-max, and that will help you get to. If you're not happy with the window that you set, just go back and adjust it so that you can see more. You know, if I wanted to see the peaks and valleys, then I will need to adjust it, but I don't really care about peaks and valleys. I just want my x-intercepts. So if I do second trace, 0. If I pick a point to the left of my x-intercept, hit enter. They put a point to the right of it, hit enter again. Now I get 6.494. So that's one critical point. My other critical point is at 12.9748. Now, technically, we don't have to test the 12.9748. Because if you look at the graph here, below the graph means decreasing. Above the graph means increasing. And below is decreasing. So 12.948 is really a relative what? Relative max, right? And it's only asking for absolute minimum. So you can test all 4 points if you wanted to, but you don't have to test this one because you know relative min has no chance of being an absolute. Relative maximum has no chance of being a absolute minimum. So you can get away with just testing the 2 endpoints at 6.9 or 6.498. But if you want to test all critical points, you're more than welcome to. I did that because I think I just treated the problem like as if I was going to find both absolute max and absolute min. So the nice thing is we already have A of 0 and A of 18 because we found A of 0 was given to us and A of 18 was we found from part B. So I can just test 6.4948 in for the t's of my W of x and R of x integral and combine that together and I'll get 525. I went ahead and I did 12.975 as well, but I didn't need to because this is a relative max. But at the very least, these are 3 candidates I'm looking at: 1200, 525, and 1310. And 525 is the absolute minimum. Now read the problem here. Sometimes they're asking you for the absolute minimum value. Sometimes they're asking you for the t value. So in this case, they're asking for the t value. So just make sure you, if you already have the right answer, just make sure that you're providing what they're looking for. So it's good to reread the problem sometimes. Okay, any questions for C? Okay, part D. For t greater than 18 hours, no water is pumped into the tank. So basically, after 18 hours, the W of T is going to stop. Okay. But there's going to be some amount of water that needs to be continually removed. So R of T is still working. R of T is still working until the tank becomes empty. Let K be the time at which the tank becomes empty. So that's the upper bound of my integral. I know I got to have R of T work from 18 hours to whenever the tank is empty. And how much is in the tank at 18 hours? How much water is in the tank? Do we know? 1310, yeah. So we know that the tank or that R of T has to continue to work until 1,300 gallons has been removed from the tank. It's not asking us to solve it, it's just asking us to set it up. So we just set up integral from 18 to K, however long it takes for this amount of water or this removal to equal out to be 1310. So that's all they're asking for part D. Okay, all right, let's go to page 10. Okay, this is number 1 FRQ, so we know this is calculator active. All right, so there's no snow on Janet's driveway when snow begins to fall at midnight. From midnight until 9 a.m., snow accumulates on the driveway at a rate modeled by F of T. So there's no snow on the ground, but then the rate at which snow is falling is this cubic feet per hour. This rate is 70 e to the cosine t. Where t is measured in hours since after midnight. Okay. Janet starts removing snow at 6 a.m. So basically, up until 6 a.m., not only is snow falling, but there's no work being done on the driveway until after 6 a.m. The rate G of T in cubic feet per hour is the rate at which Janet removes snow from the driveway in the hours after midnight. So we see that G of T is the rate at which Janet is working. So we see that between 0 and 6 hours, no work is done. She's probably still sleeping. And then between 6 and 7, she's going to start working on the driveway at a rate of 125 cubic feet per hour. So she's able to remove snow at a rate of 125 cubic feet per hour for that time interval. Now, from 7 to 9, she also works, but she's working at a different rate, a slower rate, 108 cubic feet per hour. Okay. So part A says how much snow has accumulated on the driveway by 6 a.m. So part A is usually the simplest, the most straightforward. Well, we have the rate at which snow is falling on the ground. So how can we find out how much snow there is by 6 a.m.? Take the what? Well, this is already cubic feet per hour. If we take the derivative, then we'll get cubic feet per hour per hour. How do we get the amount of snow if I'm sitting at a rate? Antiderivative, right? I want cubic feet per hour to rise up to cubic feet. So I should take the antiderivative of F of T from where to where? 0 to 6, yeah. All right, keep in mind, right? F of T is cubic feet per hour. F of T times dt means cubic feet per hour times time. If I do cubic feet per hour times hour, I'm going to be left with cubic feet. So if you're unsure which direction you should go, is it derivative or integral? Think about what's happening to your units, right? If you're at a rate, you want to move up that chain, so I gotta multiply by the time to get rid of that time to make it cubic feet. Okay, part B. Find the rate of change of the volume of snow on the driveway at 8 a.m. So this is similar to the previous problem in the sense that there are two rates going on, and we want to know which rate is winning, right? If the rate is positive, then we know there's more snow on the ground than is being removed by Janet. But if the rate is negative, then we know that that volume of snow is decreasing. So we have the two rates, we can just compare them, right? So it says find the rate of change of the volume of snow in the driveway at 8 a.m. We can find the rate of the snow falling. We can find the rate that Janet is working, and we just subtract them. If the rate is positive, you know the volume and on the ground is continually accumulating. But if G of 8 is higher, then we know Janet's work is making an impact that the volume of snow is decreasing. So f of 8, just plug that into the calculator. 7 times 8 e to the cosine of 8. G of 8 is just 125. That is the rate, so there's no need to do anything to it. It's just 125. Sorry, 108. 108. My bad. 8 a.m. is 108. So what does that tell us? That negative 59.583. Tells us that the rate of the rate of change of the snow is what? Decreasing. Yep. So the Janet's work is making an impact there. It's decreasing. Okay, cubic feet per hour. Okay, part C. Part C is a little bit more difficult, so I just want to give you a heads up there that it's a little messier. So part C says, let H of T represent the total amount of snow that Janet has removed from the driveway. So here, we don't care about how much is on the ground. We don't care about the rate at which snow is falling. We just want to track Janet's progress. Okay. So I just want to say that for her, the amount that she's able to accomplish is just whatever she's able to do up to that point, plus however much has been removed, because there's a piecewise function here. And because she's working at a different rate, we have to keep track of those different things. In cubic feet per hour, express H as a piecewise function defined by equals 9. So between 0 and 9. So what we want to do is we want to be able to plug T value, whether it's a decimal like 6.3 or 7.8, and we want to be able to find out exactly how much she's done. Okay, and so we have to do a little bit of work by hand to get there. So this is what needs to happen here. We know that initially at H of 6, that just means how much she's done at 6 a.m. right? And has she done anything at 6 a.m.? No. But we know that from 6 to 7. Right? And I don't want to put 7 here because I want to give that flexibility for, let's say if it's asking for 6.5 or 6.8 or 6.9. You want to figure out the percentage that she's done. Her work is 125 cubic feet per hour. Okay? If I take the antiderivative of this, that will give me a formula that will tell me her work in terms of how much she's removed. So we go from 6 to T. 125 becomes what? Yeah, 125x, and then we just plug in our upper and lower bound. So this formula will tell us the exact amount she's done at any decimal value between 6 and 7, right? 615, 620, 640, 645. So that's the formula for her work done between 6th and the 7th hour. Now, at 7 a.m., how much work has she done? How much snow has she taken off the ground at 7 a.m.? Exactly 125 cubic feet, right? Okay, so that means from the 7th to the 9th hour, we have a different formula because she's accomplished this much by the beginning of the 7th hour, and then from the 7th to 9th hour, she's working at a different rate. So that different rate is provided by the integral of 108 dx. We go from 7 to t, and that t can represent anything between 7 to 9. So it could be 8.1, 8.9, 7.9. We take the antiderivative. We give it that flexibility of that variable. So now we have a formula that is telling us exactly how much progress she's made in any moment in time you want to give it, even if it's a decimal value between 0 and 9. So I think that's pretty hard. So just, yeah, keep that in mind. Okay, now part D, I think this feels more comfortable with part D. Part D says, how much cubic feet of snow is on the driveway at 9 a.m.? Okay, so this, now we go back to the formula that we're more familiar with. The total amount is equal to initial plus the amount that's been added minus the amount removed. So we know that in terms of how much snow is on the ground, there's none to begin with. The amount added is from 0 to t of f of x, and so it will tell us how much snow has been put on the ground at any moment in time between 0 and 9. And then the amount removed, this h of t, is going to give us exactly how much Janet has accomplished. So we want to find out the total amount at the 9th hour. So no snow plus however much snow has been added minus, and now that we have a formula that's going to tell us the exact amount of snow that Janet has been able to remove, we just plug 9 directly into this formula here. It's between 7 and 9. Or let's say if a student was not able to figure out part C, they can still do part D because they can still know how much Janet is going to accomplish, because you know that Janet is going to do 125 cubic feet for the first hour and 108 for the second and third hour. So if you add all these up together, 125 plus 108 plus 108, that will be how much she's accomplished in that 9th hour. So we can also find that value out that way. If a student was unable to get to, figure out that formula for part C, they can still figure that information out to get to part D. Okay. Tomorrow, I'm going to check pages 7 through 10. We worked through 9 and 10, so really you only have to finish off 7 and 8, but I'll check those 4 pages tomorrow. Okay, don't get your phone.
It's on page 6.
Okay, great, thank you.